In this video, we'll discuss the systems of equations and inequalities. Now, systems of equations are a collection of two or more equations that share the same set of values that create true statements. We can often solve these three different ways using graphing, substitution, or elimination. All three methods will work, but we try to choose one that may seem easier for the situation in which we're provided, as well as one that may give us a more precise solution. Now we can use graphing as a way to find these different solution sets of a system. First, we'd want to change them each to their simplest form for graphing. For example, if we're doing lines, slope-intercept is typically the easiest. Maybe if you're working with quadratics and parabolas, you may want to change it to vertex form. And then we want to graph each line individually, or each equation individually, and then determine where do those equations intersect, and those will be the solutions for the set. If you are using your graphing calculator, you can use the intersection option to help simplify this process of finding the intersections, which will serve as your solutions. So say I have the problem of wanting to find the solutions for this system, 8x plus 4y equals 32 and y equals x squared minus 3x plus 2. First, I'd want to convert my linear equation into slope-intercept form. So if I rewrite that, I'll shift the 8 by subtracting it and divide everything by 4, and I get to y equals negative 2x plus 8. I'd graph that line, and then I'd graph the parabola. So if I graph y equals negative 2x plus 8, then I can go and graph x squared minus 3x plus 2, and you can use the vertex form, and you'll see that you end up with a graph like this. And now I'm looking at where do these two equations intersect on the coordinate plane, and what I notice is that they intersect both at negative 2, 12 and at 3, 2. So my solutions for this case are negative 2, 12 and 3, 2. So this one has two solutions as part of the system. With substitution, we recognize that we may not always be able to graph. Often if we're dealing with three or more variables, or if we notice that our solutions are not integers, it may be better to go on and use substitution or elimination. When we use substitution, we rewrite an equation for a single variable and then substitute in its expression to the other equation. And we use that to go back and find each of the values for the variables. So, say I have this system. 5y plus 51x equals 40 and 10y plus 40 equals 78x. Not exactly the prettiest of equations to deal with, so let's stick with substitution in this case. Here, I need to choose a variable from one of the two equations to rewrite. So I'm going to take the first equation and I'm going to rewrite it for y. So I'm going to subtract 51x and then I'm going to divide everything by 5, and I'd end up with y equals negative 51/5 x plus 8. Now I take that expression, the negative 51/5 x plus 8, substitute it into the second equation. And now I'm going to simplify. I distribute the 10 to everything inside the parentheses, and now I combine like terms and solve my equation. I'd end up with 120 equals 180x, and when I divide by 180 and simplify, I get that x is 2/3. So that would be kind of hard to see on a graph, because most of the time our graphs are broken down into integer values. So I now want to go back and plug that in to find the value of y. So I plug in x to either equation. It doesn't matter which one, they'll both provide the same solution. If you really want to make sure your answer works, plug it into both of them to verify that that is true. So I'm going to use the first one, plug in 2/3 for x, solve for y, and y is 6/5. So the solution for this set is 2/3, 6/5. Now elimination is another method like substitution that can be used, especially when you see graphing may be difficult or you have several variables, like 3 or 4 variables. Elimination can be very helpful. We rewrite those equations so that the variables line up, and what we're going to do is determine what variable we want to eliminate in the equations, and we'll multiply and divide each row so that the equations are added, that variable disappears or is eliminated. Once we have we solve for the remaining variable, we can then use that value to find the others. So let's go back to that same system of equations we were just looking at. In this case, first thing we'd want to do if we want to use elimination is rewrite the equation so that the y's are lined up, the x's are lined up, the constants are lined up. Now I'll look at that and I say, well, which one becomes the easiest variable to cancel? And if I look at trying to think about how could I multiply or divide, I notice that 5 and 10 are easy variables to cancel because I just have to multiply the first row by 2 to get up to 10. And if I want it to be the opposite so that they eliminate, I'd multiply by -2. So what I'm going to do then is I'm going to multiply this entire first row by -2. That creates -10y plus -102x equals -80. So now I can, when I add my two equations, I will eliminate the y variable. So I see -10 plus 10y disappears. -102x plus -78x gives me -180x, and then -80 plus -40 gives me -120. I simplify and get that x is 2/3, which is what I found through substitution. Now I can plug that back in and solve for y. And again, I can choose either of the two equations, so this time I'm going to use the other equation to solve for y. So 10y plus 40 equals 78 times 2/3. I get that 10y will equal 12, so y is 6/5. So again, the solution is 2/3, 6/5. So elimination, substitution, both will produce those same values and give you accurate answers, just maybe one will seem easier to you depending on how those variables look. Now another method that comes in very similar with systems of equations is the idea of systems of inequalities, because we will deal with inequalities from time to time. The distinction is that an inequality will bound a region that satisfies the inequalities versus specific points where the two equations intersect. So now we're looking for regions when we're talking about systems of inequalities. So this way you're typically going to be graphing your solutions. So say that I have my two original equations that I graphed before. 8x plus 4y is less than 32 and y is greater than x squared minus 3x plus 2. First thing I'd want to do is rewrite so this is in slope-intercept form. So because I divide by a positive, I know my inequality stays the same. So I have to pay attention to all my inequality rules about how I graph as I'm doing this. So when I graph y is less than -2x plus 8, I know that I'm going to have a dotted line and I'm going to shade below my line. Now when I graph y is greater than x squared minus 3x plus 2, I know that again will have a dotted line for the equation, and I'm going to shade on the inside of my parabola since it's greater than. And what I'm looking for with this system is where do those two intersect each other? Where are the shading areas intersecting? And what I recognize is that that occurs right here in this small region. So everything inside the region, excluding the lines, will be considered the solution to the system of inequalities.